the law of conservation of energy, there should be an echo. It says this: the total energy of a closed system, so total means we're probably going to be adding some stuff up. A closed system means you have no outside energy source, is neither increased nor decreased by any process. Energy can be transformed from one form to another, but the total remains constant. As an equation, we say this: the amount of kinetic energy you have at the beginning, KE initial, plus the amount of potential energy you have at the beginning, PE initial, equals the amount of kinetic energy you have at the end, KE final, plus the amount of potential energy you have at the end. Or if we include friction, the amount of energy that you have at the beginning has to equal the amount of energy you have at the end. But if it doesn't, Jeff, you lost whatever was left over to heat. Well, heat and sound and other dissipative energies, but we'll just lump that all together into heat. There's another way to think about this. If you wanted to, you could get the KEs to one side and the PEs to the other side in this equation. You could actually say PE initial minus PE final equals KE final minus KE initial. I minus the KE initial to the right and I minus the PE final to the left. Hey, what's final minus initial? Oh, no initial. Sorry, change in kinetic energy. What's initial minus final? The opposite of change in. How can I show the opposite in math? We have a lovely symbol that does that. You're overthinking it. What's our lovely symbol? What's the opposite of 3? Yeah. Another way to think about this, Miller, is whatever kinetic energy you gain, you must lose that much potential. Or whatever potential you gain, it comes at the expense of losing that much kinetic. When one goes up, the other goes down. In a closed system, if you have no outside energy sources, so you don't have a battery hooked up to this because that's adding extra energy, or you're not adding extra heat from like fire or something, a closed system. Mr. Dueck has a good demo for this. It's really why I bought the toy on the board behind me. A projectile is launched straight up into the air. If it reaches a final height of 93 meters, what was its initial velocity? Use energy to solve this. We could solve this using kinematics and vectors and all that stuff. We're going to solve this using energies. How? Is this question saying how much work? Is this question asking how much work? Read the question. Is the question saying how much work? Everybody say no. No. Is there a change in height in this question? Will there be a change in speed in this question? Yes. That's our trigger for this looks like a job for the law of conservation of energy. So if they ask how much work, I say, hey, force times distance. They didn't give me a force. Maybe there's a graph. They didn't give me a graph. Change in potential plus change in kinetic. They didn't say how much work, but there's a change in height, change in speed. This looks like a law. This looks like a job for the law of conservation of energy. So I'm going to start out by going like this. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Does this question mention friction or heat at all? Then I won't use the second version. I'll just assume this is my perfect magic physics world where everything works nice. I'm going to get a half m V initial squared, because that's what kinetic energy is, plus mgh initial, because that's what potential energy is, equals a half mv final squared plus mgh final. Oh, I notice something. What do I notice? Even before that, there's something that cancels. Okay, first thing I noticed is they didn't tell me the mass. They didn't need to tell me the mass. It turns out here, the mass cancels. But also, are any of these 0? And this is what Kai was suggesting. V final, oh, at the top for a split second, if you launch it vertically, we do come to a stop, so I can do that. Because we're starting on the ground. In fact, Riley, if I'd been particularly clever, I could have, before moving to the line that I've written in blue, I could have on here said, you know what, starts on the ground, comes to a stop. So I end up with this. 1/2 V initial squared equals GHF. What's this question ask me to find? Oh, let's get the VI by itself. How? So I'll get a 2 GH square root. Is that right, Darian? I hope. Yeah. Put your pencils down for 1 second. Look up. So before square rooting, I had this. Doesn't that look an awful lot like this? When VI is 0 or when VF is 0. This is very similar to the VF squared equals VI squared plus 2AD, which is what we would have ended up doing if we solved this using kinematics. So it's kind of popping right out. Pick your pencils up. Let's plug and chug. The initial velocity, and you'll notice I'm ditching vectors. This is scalar land, is going to be the square root of 2 times 9.8 times 93. How fast did we leave the ground at? What speed? Oh, by the way, really I should have said instead of initial velocity, should be initial speed because we're doing scalars, although we know it's up, so I guess we could add a vector direction component, Anthony, pretty easily. Come on, computer. There we go. 2 times 9.8 times 93 square root. 42.7. Mr. Dueck, why would I bother using conservation of energy for that there when I could have done it with kinematics? I would probably choose to use kinematics. But where the law of conservation of energy really shines is when you have a curvy path, like a roller coaster. So a roller coaster is traveling at 22 meters per second. If the car starts out at a height of 12 meters, how fast will the car be traveling when it gets to ground level? You know what? We're going to dulp. We're going to draw a little picture. How about like this? There's my roller coaster. There's my roller coaster. It's going to be traveling a curvy path. By the way, for what it's worth, so let me draw the ground in black. I would get the same answer if instead the curvy path went like that, like a staircase. Why? Because energy is a scalar. I will get the same answer if, in fact, the curvy path did that. I'd be going a little faster right here, but I'd lose whatever speed I gained to get back to here, so I'd still get the same answer. Or I would be getting the same answer if, in fact, my curvy path did this and then came back down, because I'd lose some speed, but I'd gain it back getting here. I'll draw a fairly simple one. So let's go with there. What else do I know? Okay. I'd be fussy. Initial speed probably, because it's a scalar, but that's okay. What else? Alex, what's this question want me to find? How fast? How fast? You'll notice this time I was a bit more careful. I didn't say what velocity, I just said how fast, which doesn't necessarily imply a vector. Is this saying how much work? Saying, okay. Is there a change in height? Is there a change in speed? Is there a yucky curvy path? Yeah. This is a job for conservation of energy. Okay. So, oh, is this question mentioning friction or heat? Does it want me to include friction or heat? Oh, it says ignore it. So my first thing I'm going to write is this. K E initial plus P E initial equals K E plus P E final. Is that okay, Jeff? And then I always ask before moving on, are any of these 0? Now I have to be careful because sometimes kids get cancel happy. We're going to go one term at a time. Is KE initial 0? Am I starting out at rest? Nope, I'm moving. Don't cross that out. Am I starting out on the ground? Nope. Am I stopping when I find my final speed? Nope. Am I ending up on the ground? So that one, I can go. So I'm going to have a half mv initial squared plus mg h initial equals a half mv final squared. O'Reilly pointed out, hey, Mr. Dueck, they told me the mass. Did they need to tell me the mass? How many of you have been on a roller coaster before? How many of you, before you got on the roller coaster, had to step on a scale to measure your mass because we had to balance everything out on the roller coaster? Now you know why. I don't know if you ever wondered that. I don't know if you ever wondered, wait a minute, shouldn't we have to be carefully be weighing everyone and making sure that, you know, I have big people next to small people and balance? Nope, mass cancels. Or it's also why an empty roller coaster car can go through the whole track and make it back to the bottom without getting stuck partway along the way. You don't need extra mass for it. Now, it is true, Jake, that if we include friction, the mass won't cancel out, but if you grease things down really, really good so that friction is nearly 0, for all intents and purposes, the masses cancel out, which is why an empty roller coaster can get through a track the same way as a full roller coaster. So I'm fibbing a bit. Technically, Sarah, the masses don't cancel, but with lots of grease, it becomes negligible, and you don't have to balance everyone out carefully. Kind of cool. Oh, what are we trying to find? Alex, what did you say we're trying to find?
How fast?
Which one? I got 2 V's. Final. Okay. So right now, I have 1/2 VI. So you know what? Let's write this down. I have 1/2 VI squared plus GHI equals 1/2 VF squared. I'm going to be clever Do you notice how there's a 1/2 in more than one term? I'm going to clear fractions. I'm going to go times by 2, times by 2, times by 2. Now, I have to multiply everything by 2, Miller. Even the middle term that doesn't have a fraction gets multiplied by 2. But why is that so nice? What's 2 times 1/2? What's 2 times 1/2? That vanishes, and that vanishes. And what I really end up with is VI squared plus 2GH initial equals VF squared. Now, Kai just went, Did you see what equation we've inadvertently derived without realizing it? Do you see it? I don't know if you remember. Oh, no, because I skipped that lesson this year stupidly. Normally, at the beginning of the year, I derive all of the equations from Physics 11, but I always skip this one. And I say, you know what? We'll do it when we get to energy. But Sarah, can you see? Don't write this down. This is VI squared plus 2AD equals VF squared. That's where the squared equation comes from. Oh, and you may recall, though, when I showed you it in projectiles, I said the problem is this is a scalar equation. It doesn't always give you a negative. Yeah, it is a scalar equation. Alex, what are we trying to find? How to get rid of a squared. Cross out the squared, put a big square root there. So V final is going to be the square root of 22 squared plus 2, 9.8, 12. Square root of 719.2, 26.8 meters per second. Oh, some built-in error checks. Hey, Carl, I know I'm going to be going faster at the bottom of the hill. So if I got an answer less than 22, I've done something wrong. Now, this is a speed. There is no directional component. Noah, I'm pretty sure it's horizontal, but I don't know for sure. I need to see a picture of the coaster. Turn the page. Or next page over. An 18-kilogram object is dropped from a height of 40 meters and strikes the ground with a speed of 25 meters per second. How much heat energy was produced during the fall? Is this question asking how much work? No. Is there a change in height? Is there a change in speed? Now, there isn't a yucky curvy path because it's dropped straight, but is this question talking about heat and energy? This is a job for conservation of energy. Only this time, they're telling me, you know what? The numbers don't balance. You lost some extra into heat. You lost some extra into heat. Are any of these 0? Am I starting out at rest? What does that mean? Yep. Am I starting out on the ground? Nope, don't cross that out. Am I ending up at rest? No! And this still is an error I'm constantly seeing. Kids are saying, oh, your final velocity is 0. No, that's after impact. My final velocity at impact, I assure you, is not 0. Don't believe me? Go outside into a field, throw a baseball straight up into the air, and let it hit your face. I guarantee you, you're going to feel it because it's got some velocity. Ah, but what's my final height? Darian, what's this question asking me to find? Oh, let's get the heat by itself then. How would I get the heat by itself, my friend?
Minus
minus. I'm glad you did that. Minus. Thank you. You know what? This is an error that drives me crazy. I think it's because the math isn't tough and kids relax. I see kids divide by KE final all the time. I don't know why. Because there's even a plus sign. Anyways, don't do that. So it's going to be, oh, you know what? It's heat. Let's do that in red because it's heat. Heat is going to be PE initial minus KE final. MGH initial minus a half MV final squared. Do the M's cancel this time? Well, there's an M in kinetic energy. There's an M in potential energy. Is there an M in heat? Nope. Nope. So the heat is going to be M18, G 9.8, H 40 minus 0.5, 18, 25 squared. Don't forget the squared. Do you get, oh, works out evenly, 1431? I'll go to 3 sig figs. You get 1,430? Is that right? Or did I miss something?
Yeah.
That's right. Units for heat, it's energy. Joules. What's example 4 asking me to find?
Work.
How much work? Oh, work is force times distance. Do you see a force or a distance in this question? No. Work is also the area underneath a force versus distance graph. Do you see a force versus distance graph in this question? What was my third definition for work? No, it wasn't conservation of energy. That's a totally different concept. It's called the work energy theorem. What was my third definition of work? This one's not on your formula sheet. This one you have to commit to memory.
Energy initial minus change potential energy plus change of
The net work that you do on an object is equal to its change in potential and its change in kinetic. Looking at this question, do you see any kind of a hill mentioned? Is there any kind of a change in height mentioned? Or does it imply that this road is flat? I think we can say for this question, ain't no change in potential energy. What's change in anything? Go equals KE final minus KE initial, which I guess is going to be a half MV final squared minus a half MV initial squared. Masses don't cancel because there isn't a mass in work, which makes sense. It does take more energy to slow or speed up a semi-truck than it does to slow or speed up a smart car. 0.5, 1,200. Oh. Problem. What's V final? 50 what? Okay, we can't use kilometers per hour. Oh, how did we switch from kilometers per hour to meters per second? It had something to do with the 3.6. You know what? I'm going to do that right in the bracket. I'm going to go 50 over 3.6, all of that squared. Why not be lazy? Minus a half m v initial, 80 over 3.6 squared. I can do that. minus 0.5 times 1200 times 80 over 3.6 squared. And I get a lovely, I think I'm going to get an, oh, yeah, I will get a negative answer. The car's lost energy. I get negative 181,000. Negative 181,000 joules. Then I said, which force does the work? Where's the energy transferred to? Heat. Heat. Turned into heat. Example 5. This one's a little trickier. Now we're going to be combining force and friction and all sorts of stuff. Let's see. Just give me 1 second. This one isn't exactly the law of conservation of energy, but it fits into kind of our thinking here. How much am I going to be getting through here? Wow. Don't know how much I'll get through today. We'll see. Example 5. An object is pushed across a level floor with mu equals 0.35 for a distance of 6.4 meters by an applied force. You know what? I think I better dulp. Although I'm not going to draw the whole thing. Instead, I am going to do a free body diagram. So there's the mass. What are the forces? Hey, this is good review. What are the forces acting on this mass? Get the obvious one. Okay, I have gravity down. Is this mass sinking into the ground? Is it flying into the air? Does this question mention any forces at angles? In other words, is this a lawnmower question? Then you know what I can say? The normal force is going to be the same size as mg. What else? There's an applied force. Okay. A says, how much work is done by the applied force? Well, work equals force times distance. Work equals, really? My pen just kicked working right in the middle of a line. That's a little strange. Pause for 1 second. Which force? The applied force. How big? Which distance? 6.4. Oh, is the distance and the force in the same direction? Then I can do work. This is not a piggyback. 58 times 6.4. 371.2. 371 joules. If you want to, you can go back and you can put a little applied beneath the F in force times distance. Sarah, what's B asking me to find? I think the work done by friction is going to be the force of friction times distance. Mr. Dueck, they're not technically in the same direction. Fair enough. In fact, the distance is this way, and friction is that way. How many degrees are there in that little line that I've drawn right there? 180. Remember, we actually said yesterday the actual equation was FD cos theta. Remember that? Of course you do. Friction is what times what? So, oh, I don't know the normal force. Oh, but look. In this question, much like in Physics 11, I know another force the same size as the normal force, which is what? And then I'll have the distance, and then I'll have cos theta. It's going to be mu 0.35 mass 12.5, 9.8 times 6.4 cosine of 180. Do you guys have a calculator on you? What is the cosine of 180? Ah, it's going to give me a negative work. I'm going to lose energy. And this is one more, Carl, way of reminding you that, okay, that does have to be in the same direction. In the opposite direction is also okay, but you're going to be losing energy to friction. And that's where the negative is coming from, that cosine equation that I gave you the other day. Crunch the numbers. What do you get when you go, it's going to be negative. What do you get when you go 0.35 times 12.5 times 9.8 times 6.4 cos 180, or times -1? Sorry? Should I? A little rap video? For now, I want to make it into an answer. Do you get negative 274.4? How much energy are we adding to the system? 371 joules. How much are we losing to friction? 274. What's left? What's the net work? Well, $371 take away 274. Is that okay, Jeff? It's actually 371.2 take away 274.4, and I get 96.8 if I go bring the sig figs back. Is that right? I think. So whoever is pushing this block, 274 joules worth is going up into heating the floor. Only 96.8 joules of work is going into changing this object's energy. How will this object's energy change? It's going to be gaining kinetic energy. If it's gaining kinetic energy, what can you tell me is happening to its speed? It's got to be speeding up. Oh, assuming the object starting from rest, what will the final speed of the object be after 6.4 meters? What did we just calculate in part C? The work energy theorem says the net amount of work is equal to the change in potential plus the change in kinetic. I think we're staying on the ground and ending up on the ground. So what I really have here is what's change in kinetic? What's change in anything? Why can I do that? Oh, it says from rest. So what I end up with is the net work equals a half mv final squared. Hey Jeff, what's this question asking me to find? Final speed. Did I say final velocity or final speed? Another hint, the fact that I picked a scalar word suggests use a scalar approach. Oh, that's going to be the VF. How would I get the VF by itself here, folks? Well, instead of dividing by a half, can I times by 2? Divide by m, square root. I think I'm going to get this. VF equals the net work times by 2, divide by m, square root. It's going to be 2 times 96 point, I think it was 96.8. Was that the net work from the previous page? Yeah? Oh, no, it means turning back. Yeah, there it is. Divided by, what was the mass? 12.5? And hey, now we're being a bit more accurate. We have taken friction into account to calculate a final speed. We probably could have done this actually using forces in this past unit. Yep. Square root. Do you get 3.94? I then said, hey, calculate the final velocity of the object after 6.4 meters using kinematics. I could. How? Look up. Given this free body diagram, could you find A, the acceleration? I hope so, because that's going to be on your next test. And once you knew the acceleration, what's VI? 0. What's the distance? 6.4. Could I find V final? Yep. That would also work. But here was an approach using work and energy as well. I could do this if I had to. You know what? I'm going to be hammering you with that stuff on Tuesday on your test. Example 6 is kind of cool, but I'm going to... Example 7. Yeah, I think I like example 7. I like example 7. I like example 7. I think so. It's twigging with me, Ben, for some reason. That I know. Says this: what average force is needed to stop a bullet of mass 20 grams and speed 250 meters per second as it penetrates wood to a distance of 12 centimeters? I could probably do this using last unit. I could probably say, well, force, mass times acceleration. Find the acceleration. They gave me the mass. I could probably say, well, V initial is 25. V final is 0. Stopped. You know what? I think I can do this a different way as well. I think I can say this. Work equals the change in potential plus the change in kinetic. And I don't think this question is talking about any change in height. I get half mv final squared minus half mv initial squared. Are any of those 0? Are any of those 0? Anthony, what am I trying to find in this question? Mr. Dueck, I don't see a force anywhere in this equation. Fair enough. Wait a minute. How else can I write work? Work is what times what? Ah, I see it now. This is going to be force times distance equals a half mv initial negative a half mv initial squared. What did you say we're trying to find?
Average force.
Oh, how would I get the force by itself? Oh, ain't so bad. Force is going to be negative mv squared. There's going to be a 1/2. That's like having a 2 there and a d. Mr. Dueck, that seems a little strange, Mr. Dueck. Actually, I think that does work out to kilogram meters per second squared. That does work out to newtons if you muck around with the units. It works. What's the negative telling me? The force is in what direction compared to the motion? The opposite. That's all it's telling me. Which makes sense. Yeah, if you're stopping a bullet, you're pushing against where it came from. So it's going to be negative 20 grams. How many kilos is 20 grams? Careful. 0.02 times 250 squared divided by 2 times 12 centimeters. I can't use that. And I get a force of negative 5,200, I guess, 10. Again, what's the negative saying? I'm not losing a force. The negative is saying, whatever direction that this bullet's traveling, the force will be applied in the opposite direction. Okay, I don't know how much this I'm going to get through, but I definitely am going to do example 8. I like example 8. I like example 8. I like example 8. Yeah, with a twist. It says a 3,000 Newton car at rest at the top of an incline, 3 meters high and 30 meters long, is released and rolls down the hill. So now we're not talking about a curvy roller coaster. This is a straight ramp, like that. Where this is 3 meters, and this is 30 meters long. Okay. No, what do they want me to find here? Speed or velocity? Suggests scalar. Is there a change in height? Is there a change in speed? I might try the law of conservation of energy, G. I might start out by saying, hey, kinetic initial plus potential initial equals kinetic, Mr. Dueck. Final plus potential, final. Noah, is this question mentioning heat or the friction force or anything? Or can I leave that off? So plus heat. Are any of these 0? Is it starting out at rest? Yep. Oh, great. Like that. Is it starting out on the ground? No. Is it ending up at rest? No. Is it ending up on the ground? Yeah, oh, cool. So I'm going to get this. mgh initial equals a half mv final squared plus heat. What'd you say, Noah, this question was asking me to find? Let's get the v by itself. I think before I divide by m or anything funky like that, what am I going to do with that heat? Okay, so I'm going to get this. mgh initial minus heat equals a half mv final squared. What did you say I'm trying to get by itself, Noah? I guess divide by m and divide by a half. Except instead of dividing by a half, I'll probably put a 0.5 down there. I get this. V final is going to be, well, squared is going to be mgh initial minus heat divided by 0.5 m. Hey, Miller, how to get rid of squared? Cross out the squared. Put a square root. Do I know the mass? Well, actually, they didn't give me the mass. What did they give me? Word begins with W. They give me the weight in newtons, but I can figure out the mass. Do I know the height? Yeah. Do I know how much heat was generated? Well, it ain't 200 because that 200, what are the units next to that 200? That's a force. What was that, Trev? Why would you? Oh, are you saying that heat is the work done by friction?
Yeah.
Where work is what times what? Oh, so are you saying that this is going to be mgh initial minus friction times distance divided by 0.5 m? I agree. Which distance, the 3 or the 30? It's got to be in the same direction as friction is acting. Which way is friction acting? Along the ramp or vertically? So, okay, it's going to be times 30. So here we go. Going to be big square root mg, which is just 3,000, because that's what the weight means, times the height, 3, minus friction, 200, times the distance that friction acts, 30, all over 0.5 times, hey, what is the mass? How can I go from 3,000 newtons to turn that into a math? Oh, heck, let's do that. Oh, heck, you know what? Let's even go 3,000 over 9.8. That was clever. 3,000 divided by 9.8 is that number there. I'll use my answer button. Bracket 3,000 times 3 minus 200 times 30, close off the top, divided by, open the bracket, 0.5 times the mass, square root. This might work out almost nice. 4.43, is that right? I hope, maybe, sort of, kind of, maybe? Didn't feel like trying it? Okay. What? 4.43 what? Meters per second. Is it 4.43?
Yeah.
You guys got that? So this gives you some ways that I can combine work, the law of conservation of energy, and the work energy theorem. I'm going to pass on Tarzan. Oh, by the way, technical comment on ramps. Because the normal force is perpendicular to the ramp, it's going to be perpendicular to the direction of motion, so the normal force does no work. Which means if we don't have friction, we can ignore the normal force. I was going to do number 10. Instead, I'm going to say, okay, homework time. Try number 1. Try number 2. 3 is good. 4 is good. 6 is good. Skip 5. 7 is good. I'll pass on 8. So right now I've assigned 1, 2, 3, 4, 6, 7.